So this is vector calculus lecture number 9. And I remind you that midterm exam 1 is in just less than 2 weeks, Monday, March 11th, in person on campus in Gillette Hall during regular class time, 11 a.m. to 12:40 p.m. We'll be doing new material today and Monday. Next Wednesday, the 6th, a week from today, we'll have a review session in class, and the exam is the Monday after that. And it covers everything up to and including what we do by the review session. So it's comprehensive in that sense. Okay. So let's review a tiny bit. We are doing vector valued functions. So we have a function R of t, which is a vector depending on this parameter, real number t. And so you can think of this as, if you're in space, you have some particle moving and its position at time t is R of t. And it's a vector with 3 dimensions, maybe x of t, y of t, z of t. If you write it in coordinates or in exactly the same thing as x of ti plus y of tj plus z of tk, where I, j, and k are the unit vectors. I is the vector 1, 0, 0. J is the vector 0, 1, 0. K is the vector 0, 0, 1. So we use these 2 notations for the vector value function interchangeably because they represent exactly the same thing. This is a vector value function in space. In the plane, you only have 2 coordinates. If you have a vector, I'm sorry. You have a vector valued function in the plane. It just has 2 coordinates. You still have your particle moving around, and R of t can be written as either x of t, y of t, or R of t is equal to x of ti plus y of tj. Right, so usually we'll deal with functions in space. It's a little bit more interesting, but functions in the plane are fine also. Let me do a couple of the homework problems that I've assigned so far in this chapter. So in section so some homework problems. In section 14.1, number 9, find the function R of t that describes the line through the points P and Q P has coordinates 2, 3, 7, and Q has coordinates 4, 6, 3. So if you want to find the line through a point P with coordinates x, y naught, z naught in the direction of the vector ABC, which is not the zero vector, the equation of that line is R of t is, well, the first coordinate is x naught plus at. Second coordinate is y naught plus bt. And the third coordinate is z naught plus ct. That's the equation of the line. These are the parametric equations of the line. Now, in this problem, we have 2 points we can choose as the point through which the line passes, but we don't have the direction. But because we have 2 points, this is the point P and this is the point Q, the line going through them is in the direction from P to Q. The vector from P to Q, it's really Q minus P. It's 4, 6, 3 minus 2, 3, 7. So that's 4 minus 2 is 2. 3 minus 6 is minus 3. And 3 minus 7 is minus 4. So this is the vector ABC. So the equation of this line is R of t is equal to x naught. I can take 2, 3, 7 for x naught, y naught, z naught. So this is 2 plus 2t, 3 minus 3t, 7 minus 4t. So this is the line through these 2 points. When t is equal to 0, where is the point on the line? R of 0 is 2, 3, 7, which is the point P. At time t equal 1, the position of the particle, when t is 1, you get 4. Oops, something isn't right here. 6 minus 3 is plus 3. That's better. When t is 1, I get 3 plus 3 is 6. And when t is 1, 7 minus 4 is 3. This is the point 463. This is Q. So this line passes through the points P and Q. At time 0, it's at P, and 1 second later, at time t equal 1, it's at Q. Any questions about this? These are all sort of like basic questions about vector valued functions and lines that you could be asked on the midterm. Let's look at in section 14.1, number 11. We want to find the equation of the line, a function R of t, that of the line through the point P with coordinates 3, 4, 5, and orthogonal to the plane 2x minus z equals 4. So the picture is, here we have this plane, 2x minus z equals 4, and we want to find the line perpendicular to the plane and passing through the point P with coordinates 3, 4, 5. You'll notice this point doesn't lie on the plane, but there's a point in space, and you want to find the line perpendicular to the plane going through this point. So must find a vector perpendicular or orthogonal, these mean the same thing, or normal to the plane. So we have to recall how we define a plane. So how do we find the plane through the point x naught, y naught, z naught with normal vector? Let me just go back and check the notation that we use for this. So with a normal vector n, having coordinates a, b, c. So if this is the plane, the normal vector n is perpendicular to the plane. So in order to find if your line is perpendicular or normal to the plane, it's going in the direction of the normal vector to the plane. Now, the equation of the plane with going through x naught, y naught, z naught with normal vector ABC is a x minus x naught plus b y minus y naught plus z plus c z minus z naught equals 0. This means all the points where x, y, z, x naught, y naught, z naught is a point in the plane, where this vector is perpendicular to this vector, so the dot product is 0. Or another way of writing this is ax plus by plus cz equals some number d. Now, where is our plane? Our plane is 2x minus z equals 4. That's like 2 times x plus 0 times y plus minus 1 times z equal 4. So for this plane, the normal vector n has coordinates 2, 0, minus 1. And this is the direction vector of the line. So we want the line passing through the point P with coordinates 3, 4, 5 in the direction of the vector 2, 0, minus 1. So this line R of t will be 3 plus 2t. That's the first coordinate. Second coordinate is 4 plus 0t. And the third coordinate is 5 minus t. 3 plus 2t, 4, 5 minus t. Any questions about this? All right, let's do some more of these exercises. It's also kind of early review for the exam, but that's good. Number 15. We have the vector valued function in the plane given by r of t is 2 cosine t, 2 sine t, as t goes from 0 to 2 pi. So on this curve, the first coordinate x of t is 2 cosine t, and the second coordinate y of t is 2 sine t. Now you should recognize these. For one thing, if you take x of t squared, that's 4 cosine squared t. Y of t squared is 4 sine squared t. So x of t squared plus y of t squared is 4 cosine squared t plus 4 sine squared t. If you factor out the 4, that's 4 times cosine squared t plus sine squared t. Cosine squared plus sine squared is 1. 4 times 1 is 4. So every point on this curve satisfies the equation x squared plus y squared equals 4 or 2 squared, which is the equation of a circle of radius 2. And when t is equal to 0, you have 2, 0. You're at this point. And as t goes from 0 to 2 pi, you're moving around the circle, and at 2 pi, you're back exactly where you started. So if you want to think of this as a particle moving in the plane, it starts at the point 2, 0, and as t goes from 0 to 2 pi, the particle is moving around the circle. It makes one complete revolution and ends up right back where it started. That's kind of nice to see. What about number 17? In 17, we're in the plane. Our vector value function r of t is 2t, is t, comma 2t, for t going from 0 to 1. So when t is 0, you're at 0. When t is 1, you're at the point 1, 2. In fact, in this x is equal to t, y is 2t, t is x, this is y equals 2x. So you're just moving along the line, y equal 2x. This point, r of 0 is 0, 0. R time 1 is 1, 2. You're just moving along this line. That's the curve traced out by this function. And the arrows indicate positive orientation, which means the direction the curve is, the particle is moving as t increases. Problem 21, you're looking at a curve in space. R of t is cosine ti plus j plus sine t k. As t goes from 0 to 2 pi. So in this curve, x of t is cosine t, y of t is always equal to 1, and z of t is sine t. And if x is cosine and z is sine, x of t squared plus z of t squared is cosine squared t plus sine squared t is equal to 1. So your curve, let's see, first of all, this is the x, y, and z axis. You're actually always working in the plane this is 0 and this is 1 on the y-axis. Y is equal to 1. So you're always sitting in this plane, which is parallel to the xz plane. And in this plane, as t increases, you're moving around the circle of radius 1. So if this is the positive x direction and this is the positive z direction, you're moving like this in this plane. It's what we call a coordinate plane. It's parallel to the xz coordinate plane. So all the points with y equals 0. And as x at time 0, you're right here. This is r at time 0. And it's also r at time 2 pi. And as time increases from 0 to 2 pi, you're going around the circle. This is the positive orientation. And you end up out where you started. Let's look at the next problem in the homework, which was problem 31. These are limits. Find the limit as t goes to pi over 2 of cosine 2ti minus 4 sine t j plus 2t over pi k. So the way you take the limit of a vector valued function is to take the limits of the coordinate functions. So the limit cosine 2t as t goes to pi over 2, as t goes to pi over 2, 2t goes to pi, and cosine pi is minus 1. The limit as t goes to pi over 2 of 4 sine t, sine of pi over 2 is 1, 4 times 1 is 4. And the limit as t goes to pi over 2 of 2t over pi, well, this is 2 over pi times pi over 2 is 1. So this limit is minus 1i plus 4j plus k. As t goes to pi over 2, you just take the limits of each of these coordinate functions. Oops. Minus 4. Any questions about this? Number 33 is exactly the same type of problem. You're taking the limit as t goes to infinity of e to the minus t I plus 2t over t plus 1 j minus plus the inverse tangent of t, k. So you have to take the limit of each of the coordinate functions. What is the limit of e to the minus t as t goes to infinity? The graph of e to the minus t looks like this. It's decaying as t goes to infinity and approaching 0. What's the limit of 2t over t plus 1 as t goes to infinity? Let's see, I can write this. If I divide this by t, this is 2 over 1 plus 1 over t as t goes to infinity. As t goes to infinity, this goes to 0, so the limit is 2. What is the image? The limit is the inverse tangent of t, or the arctangent of t. As t goes to infinity. Now let's see. Remember, the tangent is sine t over cosine t. And this is 0 when the cosine is plus or minus pi over 2. If you graph the tangent from minus pi over 2 to plus pi over 2, the graph of the tangent, it's 0 at 0, and as t approaches pi over 2, this is going to 1, and this is going to 0. This is going out to infinity. And minus pi over 2, this is going to minus 1, and this is going to 0. It looks like that. That's the graph of the tangent. And the graph of the inverse tangent of t looks like that. This is pi over 2. This is minus pi over 2. As t goes to infinity, the arctangent or the inverse tangent approaches pi over 2. So this limit is 0 times I, 2 times j, and pi over 2. Okay. Always helps to write the problem down correctly. This was a minus sign in the problem. So this is going to minus 2. That's correct. Again, it's you have to know Calc 1 and Calc 2 to pass Calc 3. Okay. So those are all the homework problems from section 14.1. Let's do some of the problems from section 4.14.2. I had started off by assigning 9 to 23, the odd numbered problems, and then some more. So here there are more problems because this is really the calculus. This is what we have to learn. So let's look at problem 9. We have the vector valued function r of t is equal to cosine t, t squared, sine t. You differentiate a vector valued function by differentiating the coordinate function separately. So r prime of t, derivative of the cosine, is minus the sine. Derivative of t squared is 2t. Derivative of sine t is cosine t. That's all there is to it. Problem 11. R of t is 2t cubed, 6 square root of t, 3 over t. So r prime of t, the derivative of t cubed, is 3t squared. So this is 2 times the derivative of t cubed, 3t squared. This is 6 root t, this is t to the 1/2. So this is 6 times t to the minus a half. And this is 3t to the minus 1, that's minus 3t to the minus 2. So this is 6t squared, 3 over the square root of t, minus 3 over t squared. Let's do one more, say number 15. The vector valued function r of t is t e to the minus t, t times the log of t, and t times the cosine of t. So we have to differentiate each of these coordinate functions. The derivative of t e to the minus t, by the product rule, is the derivative of t, which is 1 times e to the minus t, plus t times the derivative of e to the minus t, which is minus e to the minus t. So this is 1 minus t, e to the minus t. So if there's any question about how you do these derivatives, just interrupt me and ask us. The derivative of t log t, again by the product rule, is the derivative of t, which is 1 times the log of t, plus t times the derivative of log t, which is 1 over t. So this is log t plus 1. And the derivative of t cosine t is the derivative of t, 1 cosine t, plus t times the derivative of the cosine, which is minus the sine of t. So for this function, the derivative r prime of t is 1 minus t e to the minus t, comma, log t plus 1, comma, cosine t minus t sine t. That's what it is. So a tangent vector is just another name for the derivative of a vector valued function when the tangent vector is not 0. So if we have, for example, let's say number 21, we have the parametrized curve or the vector valued function R of t equals 2t to the fourth I plus 6t to the 3/2 j plus 10 over t k. And we want to find the tangent vector at t equal 1. So r prime of t, when you differentiate 2t to the fourth, you get 2 times 4, which is 8 t cubed I. The derivative of t to the 3/2 is 3/2 t to the 1/2. 6 times 3/2 is 9 t to the 1/2. And the derivative of 1 over t is minus 1 over t squared. So this is the tangent vector at t, and at t equal to 1, r prime at t equal 1 is 8. Get my j here. 8i plus 9j minus 10k. So that's the answer. Problem number 3 is to find the unit tangent vector. So you take the tangent vector at a point on the curve, divide by its length to get a vector of length 1 pointing in the same direction as the tangent vector. So if r of t is the vector valued function, 2t, 2t, t, then r prime of t, you just differentiate each coordinate, 2, 2, 1. This is a constant vector. The length of r prime of t is the square root of 2 squared plus 2 squared plus 1, which is 4 plus 4 plus 1. That's 9. Square root of 9 is 3. So the unit tangent vector is 2/3, 2/3, 1/3. That's usually denoted with a capital T. Then some of the remaining problems in this section are to use the derivative formulas to calculate derivatives of vector valued functions. If we look at number 49, we have the function, well, we have a dot product of two vector valued functions. We have t squared times the we have t squared times the vector. Looks like there's a typo here. I assume this should be I plus 2j minus 2tk. So it's this vector times the scalar. And then we have another vector, e to the ti plus 2e to the tj minus 3e to the minus tk. And I'm taking the dot product of those vectors, which is a scalar, and I want to differentiate that. And I want to use the derivative rules to compute this derivative. So the derivative of the dot product of two functions is the dot product of the derivative of the first times the second plus the first times the derivative of the second. So let me do it like that and see what I get. So if I differentiate this first function, this is really t squared I plus 2t squared j minus 2t cubed k. Now let me just do it like that. So when I differentiate this, I get 2ti plus 4tj minus 6t squared k. Dot product with the second function. Plus the first function, this one, t squared I plus 2t squared j minus 2t cubed k, dot product with the derivative of this. The derivative of e to the t is e to the t. The dot product of 2e to the t is 2e to the t. And the dot product of e to the minus t is minus e to the minus t. Minus times minus is plus. This is plus 3e to the t k. So if I take these dot products, I get some long, messy thing. The dot product of this and this, I multiply coordinates and add. I get 2t e to the t plus 8 t e to the t plus 18 t squared e to the minus t. When I take the dot product of this, I get t squared e to the t. 2t squared times 2 is 4t squared e to the t. Minus 2t cubed times 3 is minus 6t cubed e to the t. So this is now just a scalar. If I factor out the e to the t, let's see what I get. I get 2t plus 8t is 10t. I have 18t squared. Oh, sorry, I can't factor out e to the, I have e to the minus t there. It's minus e to the t. That's right. So then I have t squared plus 4t squared. I have plus 5t squared e to the t. And then I have e to the minus t times 18t squared minus 6t cubed. So you do the calculation and hope that it's okay. If you want to have the answer look the way it looks in the back of the book, from this first expression, you factor out the 5t, you get 5t e to the t times 2 plus t. And from this, you can factor out 6t squared e to the minus t b minus t. And that's exactly what it is. So, unfortunately, sometimes you have to do a little bit of work. Let's do a couple of problems from this homework involving integrals. So 71 is compute the definite integral from -1 to 1 of I plus Tj plus 3t squared k dt. So we separate this into the x, y, and z coordinates. This is the integral from -1 to 1 of 1 dti plus the integral from -1 to 1 t dtj plus the integral from -1 to 1 3t squared dtk. The integral of 1 is t, so this is t evaluated from -1 to 1 I. The antiderivative of t is a half t squared, evaluated from -1 to 1 j. The integral of 3t squared is t cubed, evaluated from -1 to 1 k. So this is 1 minus 1. This is 2i. This is 1 minus 1 is 0j. And this is 1 minus 1 plus 2k. So that's what it is. Or if you want to write it in coordinates, 2, 0, 2. Problem number 77 is the integral from 0 to 2 of t e to the minus e to the t times the vector I plus 2j minus k dt. That's the same as the integral from 0 to 2 of t e to the ti plus 2t e to the j e to the t j minus t e to the tk. And again, we write this as the sum of three integrals. The integral from 0 to 2 t e to the ti plus dt plus 2 times the integral from 0 to 2 t e to the t dt j minus the integral from 0 to 2 t e to the t dt k. You could actually write this as the integral from 0 to 2 t e to the t dt times the vector I plus 2j minus k. In any case, we have to integrate from 0 to 2 t e to the t dt. I would integrate that by parts. If this is t and this is e to the t, this is 1 and this is e to the t. So this is t e to the t evaluated from 0 to 2 minus the integral of e to the t dt from 0 to 2. What is this equal to? When t is 2, you get 2e to the t. When t is 0, you get 0. This is minus e to the t evaluated from 0 to 2. Sorry, this is 2e squared minus 0 minus e to the t evaluated from 0 to 2. That's e squared minus 1. So this is e squared plus 1. So what we get is e squared plus 1 times the vector I plus 2j minus k. In coordinate form, if you like, e squared plus 1 times the vector 1, 2, minus 1. Oh, wow, okay. So this is actually most of the homework that's due next Monday, but since we're getting close to the exam and these are important skills to acquire, derivatives and integrals of vector valued functions, I'm glad I had a chance to go over this. Okay. The next topic we discuss is 14.3.
Professor, I have a question.
Go ahead.
I don't think you uploaded the homework that's due on Monday.
Oh, then I will do it as soon as class is over.
Okay, thank you.
Yeah, let me just double check one thing. Just looking at Blackboard right now. Okay, just 1 second. For vector calculus. Oh, you're right. I'm sorry. Huh. Um, okay. Yeah, it's there now. I just put it up. Thank you. I thought I had done that a long time ago. Okay. 14.3, motion in space. So I talked about this a little bit on Monday, and I will go through it again. So the magic words are position, velocity, speed, and acceleration. So the position of a particle moving in space or in the plane, but moving in space, is simply given by a vector value function r of t with coordinate functions x of t y of t, z of t. So that's the position of the particle at time t. Often starting at time t greater than or equal to 0, t equals 0, that's, you might call that the initial position, but could be negative values of t also. The velocity is v of t, which is the derivative of r of t, just the position vector. It's just the derivative vector, the tangent vector. This is x prime of t, y prime of t, z prime of t. And speed, see, position and velocity are vector valued functions. Speed is a scalar valued function. It's just the length, the magnitude of the velocity vector. So that's the square root of the sum of the squares of the coordinates of the velocity. X prime of t squared, y prime of t squared, z prime of t squared. And acceleration, velocity is the rate of change of position. Acceleration is the rate of change of velocity. So the derivative of the velocity, but the velocity is the derivative of the position. So it's the derivative of the derivative, or the second derivative is the acceleration. Let's look at an example. Here's a pretty example, which you will find in the text. So the position of a particle moving in time is called its trajectory. So consider the following trajectories. You have the particle whose position at time t is given by t squared minus 4, and t cubed over 4 minus 8. And you have another particle whose position at time t is given by the position function. These are vector functions. R of t is t squared, t to the 4th minus 4, t to the 6th over 4 minus 8. And we want to look at both of these trajectories for t greater than or equal to 0. So at the starting point at time t equals 0, r of 0 is at 0 minus 4 minus 8. And capital R of 0 is also at 0 minus 4 minus 8. So those two particles are starting at the same time. At time 4, R at time 4 is at the position 4. 4 squared minus 4 is 16 minus 4 is 12. 4 cubed is 64. 64 over 4 is 16. 16 minus 8 is 8. So this particle starts at 0 minus 4 minus 8, and 4 seconds later is at the point 4, 12, 8. This particle at time 2 is at position 4. 16 minus 4 is 12. 2 to the 6th is 64 over 4. 16 minus 8 is 8. So it's at the same position as the first particle, but the first particle takes 4 seconds to get here. The second particle takes 2 seconds to get there. In fact, if you look at these functions, little r at t squared is capital R at t. So there's this kind of curious relationship between them. What are their velocity vectors? So for the first function, the velocity, when you differentiate with respect to t, is derivative of t is 1. Derivative of t squared minus 4 is 2t. Derivative of t cubed over 4 minus 8 is 3t squared over 4. For this function, I'll write that with a capital V for the velocity of the capital R of t function. When you differentiate with respect to t, you get 2t, 4t cubed, 6t to the 5th over 4, which is 3t to the 5th over 2. That's what it is. Let's look at a few more interesting problems. Again, historically, the origin of most of calculus had to do with these types of elementary physics problems having to do with motion, position, velocity, acceleration. I'm going to look at example 3 in this section on motion in space. This is going to be motion on a sphere. So I'm going to try to show that a certain path is a path on a sphere. So the position at time t of a certain particle in space is going to be 3 cosine t, 5 sine t, 4 cosine t. As t goes from 0 to pi. So this is a curve that comes around on itself because r at time 0 is 3 cosine 0, 3 times 1 is 3, 5 sine 0 is 0, 4 cosine t is 4. And if you take r at time 2 pi, cosine of 2 pi is 1, sine of 2 pi is 0, cosine of 2 pi is 1. So at time 0 and at time 2 pi, you're at the same place, and somehow you are moving in space and you come back to where you started. Now, at any time t, what is the distance? What is the length of this vector? The length of this vector is going to be equal to the square root of the sum of the squares of the coordinates. 3 cosine t squared plus 5 sine t squared plus 4 cosine t squared. That's the square root of 9 cosine squared t plus 25 sine squared t plus 16 cosine squared t 9 plus 16 is 25. This is the square root of 25 cosine squared t plus 25 sine squared t. And factor out the 25. Cosine squared plus sine squared is 1. This is the square root of 25, which is 5. So this point always lies on the sphere around the origin, whose radius is 5. So if you take the length of this vector, it's identically equal to 5 for all t. So here you have the sphere, and you have some curve on the sphere coming back on itself, but it's always on the surface of the sphere. What is the velocity of this particle? You differentiate. Derivative of cosine t is minus sine t. Derivative of sine t is cosine t. Derivative of cosine t again is minus sine t. So this is the position of this is the velocity anytime. And the speed, which is the length of the velocity, is the square root of the sum of the squares of these coordinates. 9 sine squared plus 25 cosine squared plus 16 sine squared. Again, it's 25 sine squared plus 25 cosine squared is exactly this. This is 5. So this particle is moving with constant speed 5 on the surface of the sphere. Let's just recall Newton's second law of motion. It says force equals mass times acceleration. So if you have a particle with mass m, position r of t, then the acceleration is the second derivative of r of t. So you have mass times the second derivative of r of t is equal to, I'll write it like this. This is the sum of all the forces acting on your particle. If it's one force, it's one force, but if it's more, it's more. So if you know something about the forces, this tells you something about the acceleration. And if you know the acceleration and you integrate, you get the velocity. And if you know the velocity and you integrate, you get the position. So let's just take a look at an example of how one does this. So the simplest force is gravity. Gravity is a force pointing downwards. This is the force of gravity. Minus, if you're working in the plane, this is minus mg j. Or if you want to write in coordinates, so force is minus mg j, or 0 minus mg. There's no component of this force in the horizontal direction. It's strictly pointing down. Where you might remember from calculus that the acceleration due to gravity is 9.8 meters per second squared, or 32 feet per second squared. So Newton's law, when the force is gravity, says mass times acceleration at time t is the force, which is 0 minus mg. Actually, you can cancel the mass, you get the acceleration is 0 minus g. So the velocity is, the derivative of the velocity is the acceleration. So the velocity is the integral of the acceleration, which is the integral of 0 minus g dt, which is 0 minus gt plus some constant. And the derivative of the position is the velocity. So the position is the integral of the velocity, which is the integral of 0 minus gt dt. Which is 0 minus a half gt squared plus a different constant. I call this constant u naught v naught. This is u naught v naught minus a half gt squared. And this is the form that you see in the textbook. Let me just go through this again, because this is really exactly what you learned in Calc 1. So you have the force due to gravity is 0 minus mg. And you know that mass times acceleration is equal to the force. And if the acceleration is the acceleration due to gravity, or the force of gravity, this is 0 minus mg, which is the same as m times 0 minus g. So you can cancel the m's, and you get the acceleration due to gravity is 0 minus g. So the velocity is the integral of 0 minus g dt. Which is 0 comma minus gt plus a constant. Let me write this constant as u0 v0. So this is equal to u0 v0 minus gt. And then the position is the integral of the velocity. That's the integral of u0 v0 minus gt dt. If I integrate this, the integral of a constant u0 is u0t comma v0t minus a half gt squared plus some other arbitrary constant, which is the initial position. Let me just write this as x naught, y naught. So the position at time 0 is x naught, y naught. The velocity at time 0 is u naught, v naught. So this is u naught t plus x naught, y naught plus v naught t minus a half gt squared. I'll talk about this again a little bit more on Monday, but there's just one other thing I want to introduce, and in some sense, the sooner the better. It'll all be part of the homework for next week, and it's the last topic, which is covered on the midterm, which is we have some curve in space described by some particle r of t. So suppose r of t, this position at time t, has coordinate functions f of t, g of t, h of t. And we're interested in this curve as t goes from A to B. So this is r at time 0, and this you end up at r at time b. And how long is this curve? What is the distance traveled? So the length of the curve is given by the formula L, which is the integral from A to B of the square root of the sum of the squares of the derivatives of the coordinate functions. dt. This is the integral from A to B. If you look at this exactly, you'll see this is exactly the velocity function, the speed. So these are equivalent formulas, and it doesn't matter which one you know or don't know, but that's what they are. And in general, these are hard integrals to evaluate. But sometimes they're not so hard. And we'll also talk about this on Monday, the length of a curve. Okay. All right, so the exam goes up to and include section 14.4 on the length of curves, and that's the whole story for us. Any questions about any of this? Okay. There are office hours. There's one tomorrow at 7 p.m. Friday at 4:30 p.m. And if you have questions and you can't make either one of those office hours, send me an email and we can work out something. Someone's asking if there's a practice exam. That's a good question. Maybe I'll put together one and we'll go over it on the review session next Wednesday. That's not a bad idea. Okay. All right. Be well. I'll see you. Next class is Monday.
Thank
Bye.
you again, Professor. Have a good day.
Thank you. You
Have a
too.
good
Thank you.